Warahmatullahi ta'ala wabarakatuh, and good day everyone. Alright, so today we come to the second part of a synchronous lecture for chapter 5. Okay, so I may consider this as part 2 for chapter 5, partial differential equations. Okay. Alright, so where did I by now I assume all of you have dah tengok video saya yang part 1 and part 2 that I have uploaded last week, because you need to understand, okay, what we have discussed so far, where for example 3 and example 4 I have used the method of separation variables, okay, where we are able to separate and come out with two differential equations with one variable boundary conditions. Okay, but we have not yet find the solution of this partial differential equation for both example 3 and example 4. But by now, the learning outcome for part 1 have been achieved. I assume all of you know already the steps on how to separate the PDE into ODE with one independent variable each. Okay, with one independent variable each. Okay, as what you can see in this example 3 as well as example 4 here. Okay, so to recap back, kalau tengok, okay, in order to solve for PDEs, there are altogether 4 steps. As of now, okay, we just done with step number 1. Okay, just done with the step number 1. However, step number 1 ni dia agak panjang juga. So for today lecture, part 2, we are going to complete all the remaining steps. Step number 2, step number 3, as well as step number 4. Okay, clear? Alright, okay. Okay, so the remaining steps, number 2, 3, and 4, there are two ways of solution, especially on step number 3 and 4, where we can use solving heat equation or using the Fourier series solution. Okay, Fourier series solution. This is where I've mentioned to you before in chapter 4. I keep on saying that chapter 4 is important for chapter 5. This is where we are going to apply what you have learned in chapter 4. Okay, alright, so so far, okay, what I have just summarized tadi, okay, we have done with the use separation of variable technique to get two ODEs with one with one variable boundary condition. Okay, that's what have been covered in chapter 5 part 1. Okay, so now what we are going to do, we are going to solve those ordinary differential equation to obtain the solution for UXT. Okay, so I'm not going to repeat all the steps again. Just refer from example 3. Sekarang ni this example 3 je saya jadikan di example 5. Okay, the same question as in example 3. Okay, from example 3, we have come out with two ODEs. Okay, this is actually the questions. Okay, this is the questions. So the first ODE is del T GT plus with lambda k gt equals to 0, which is this is a first order differential equation, and the second differential equation is a second order because we have del square vs del x square plus lambda vs equals to 0, and the initial condition is v0 equals to 0, and the boundary is vl equals to 0. So sekarang ni apa yang kita perlu buat? Okay, first differential equation kita nak cari what is GT. Second differential equation we want to solve for Vx. Dan dari situ nanti kita dapatlah what is our UXT. UXT kita adalah Vx darab dengan GT. Tu konsep dia. So make sure all of you boleh faham maksud dia ni. Okay, so now kita cuba selesaikan yang senang dahulu, which of course yang mana yang senang? Of course yang first order lah yang senang kan. Okay, the first order here. Okay, so sekarang ni kita ada del over del t, saya guna dg over dt terus lah. Okay, plus with lambda kgt, yang ini dalam respect to t kan, equals to 0. So daripada sini we use the first order separation method. Hopefully all of you ingat lagi. Okay, sepatutnya kena ingat lah sebab kita nak guna ni. So we are going to separate. We have two things here. We have G dengan T. Kalau sebelum ni biasa kita ada Y dengan X. Okay, so sekarang ni apa yang kita ada? Kita ada dG over dt equals to, saya nak separate T dengan G. So we have lambda kg. Lambda kg. So then dari sini kita ada G ni boleh bawa ke belah kiri. So we have 1 over G dg equals to negative lambda k dt. So nampak we have separate G and T just like our first order separable method. Kalau yang blur-blur yang ni boleh refer balik chapter 2. Okay, so we introduce integration on both sides. So 1 over G with respect to G, we integrate, we get ln G. And this one negative lambda K is just a constant kan. So negative lambda K ni boleh letak kat luar. So as if that you are integrate 1 respect to dt. So you have negative lambda K T plus with C. Alright, so ln G here. So kita nak cari what is G. So again using the exponential punya, tukar dari bentuk ln kepada exponential. There you go, we have e to power of negative lambda kt plus c, which is yang ni sama juga dengan negative e to power of minus lambda kt darab dengan e to power of c. And you boleh kecilkan dia, boleh ringkaskan dia jadi, okay, sekejap saya nak tulis cantik-cantik. Okay, boleh ringkaskan dia jadi G ni sama dengan C e to power of minus lambda k t. Nampak? Okay, e to power of c ni you can just regard as a big C. So there you go, boleh nampak kat sini. Okay, lambda ni kita ganti dengan lambda n. Okay, lambda n. Nanti tak apalah. Sekarang ni nak letak lambda pun dulu pun tak apa. No big deal. Later you will understand kenapa jawapan dia tu bertukar jadi lambda n. Because we are not yet coming to the final answer. Nanti lambda ni panjang lagi cerita dia. Alright? Okay, so far now semua orang dah faham macam mana untuk dapat G. G simple. Okay, GT ataupun G lah. Same thing. Alright, so now let's proceed to how to get Vx. Okay, untuk Vx, we have del square Vx over del x square. Okay, plus with lambda Vx equals to 0. And we have the initial condition V0 equals to 0 and the boundary condition VL equals to 0. Okay. From here, yang ni daripada sini kita tukarkan dia ke dalam bentuk, okay, semua orang boleh faham kan? Okay, from V del square over del x square Vx ni jadi V double prime. That double prime indicates that this is second order derivative plus with lambda V. Okay, lambda V ni maknanya V ni is only a function, bukannya kata V ni is apa ni, dia punya tak ada derivative pun. Okay, tak ada derivative pun. Okay, so you may convert this into its characteristic equation just like what we have before. Kalau kita sebelum ni kan kita ada y double prime plus with 4y for example equals to 0. So if this is the case, then you are going to convert this into its characteristic equation. You dapat apa? R square tambah 4. R ke tambah 4? Tambah 4 sahaja. Sebab ni bukan y prime. Kalau lah benda ni y double prime plus 4y prime equals to 0, yes, this is going to be r square plus r equals to 0. Nampak beza because this is y prime first derivative, but this is a normal function. So that's why here jadi 4, bukannya 4r. So same goes here. This is v, not v prime. So we have r square plus with lambda equals to 0. Then daripada sini kita akan dapat our R is equals to plus minus of negative lambda. Plus minus of negative lambda. Do we know what is our lambda value? No, we have no idea what is our lambda value. Okay, up to this step semua orang boleh faham ya. From the second order derivative equation, we convert it into its characteristic equation and we come out with R is equals to plus minus root of minus lambda. However, we have no idea what is our lambda value. It is an unknown value, but we may consider 3 cases for lambda. So dari sini, for us to determine the solution for Vx, sebenarnya the most important thing, it is rely on lambda ni. Okay, we have no idea for lambda, but we are having 3 cases to consider for lambda. If our lambda is more than 0, then ni dia punya solution for our Vx. Okay, C1 equals Vx equals to C1 cos lambda root of lambda x plus C2 sine of root lambda x. If our lambda equals to 0, then our V is equals to C2 plus C1 x. Okay, and if our lambda is less than 0, then this is our solution for our Vx. C1 cos root of minus lambda x plus C2 sin root of minus lambda x. Okay. Solution for each case of eigenvalue is checked based on the boundary condition yang kita ada. The initial condition yang ni dan boundary condition yang ni in order to determine the eigenfunction and obtain the solution of Vx. Saya tak pastilah you all faham tak apa yang saya cakap ni, but I'm sure you will understand bila kita expand example 5 very soon here. Okay, so ibarat kata sekarang ni you just faham. Okay, we know that our R is equals to plus minus root of minus lambda, tapi kita tak tahu lambda kita ni apa value dia. Sama ada lambda kita tu katakanlah lambda kita more than 0. Okay, more than 0, negative 4, negative 5 and so on. So masuk dalam ni. Okay, then we will get this is our solution. If our lambda equals to 0, then this is our V. Then if our lambda is less than 0, then this is our V. So bila dah dapat jawapan what is our V, then kita boleh masukkan V ni untuk didarab dengan G yang kita dah cari tadi. So then this is our solution. Okay, macam mana? Maknanya sekarang ni saya dah bagi jawapan akhir ni. Kita punya Vx ni tiba-tiba je sama dengan Bn sin n pi x over L. Dari mana dapat benda ni? Dari mana dapat benda ni is what I'm going to discuss very soon. Okay, actually this one Vx equals to Bn sin n pi x over L ni is coming from one of these 3 cases. How to check whether your solution is one of these 3 cases is by checking the condition V0 equals to 0 and VL equals to 0. How to relate this condition dengan 3 cases here is your next learning outcome. Okay, we will go through together very soon. So make sure you are able to understand how to check each of these 3 cases by using this boundary conditions. Alright, okay, we're gonna do this in the next video.